So for now, let's get back to rotational motion. Here's what we've got, right? So far, let's take a look at everything that we know. Kinematics, dynamics, we've seen them in linear, we've seen them in rotational. We've got them down, right? Really, everything can be summed up pretty well right here. Now, conceptually, you've maybe touched upon energy and momentum just a little bit, but not quite in depth quite yet. So, of course, the theme of the day, to no great surprise to anybody, is let's fill in this next picture right here. Let's figure out what is energy going to be doing in rotational motion. So let's go back to our lopsided dumbbell picture. Right, when we had that thing moving around, clearly it's spinning. It has some kinetic energy, right? Movement. You see movement, you know that there's going to be kinetic energy, right off the bat. I don't need to worry about that. How do I actually quantify that kinetic energy? Well, the way that we know how very well right now is 1/2 mv squared. So let's do that. Well, let's just try that and see what it gets us. Take block 1, take block 2. 1/2 mv1 squared, 1/2 m2v2 squared. Okay. Well, now you might remember that there's this little transformation that says v is equal to r times omega. All right, well, what is the r? It's unique for each one of these because we remember that it's spinning about the center of mass right there. So I've got r1 on the left side, r2 on the right side. So now I've got 1/2 m1 r1 omega squared, but it's the same omega in each because remember, it doesn't matter where you're at in the circle. If you're spinning around in the circle, you've got the same omega. Well, then let me pull the omega to the outside. Pull omega to the outside, now I'm left with m1 r1 squared plus m2 r2 squared. Remember here that for any point mass spinning about a point, its moment of inertia is mr squared. If I have two objects, that means I'll have an m1 r1 squared, m2 r2 squared. That's rotational kinetic energy. That's where we're getting this from. Now, let's imagine this is not the only type of kinetic energy that we can have, and I've led on to this before, right? Where I've talked about the fact that we can have more than one variety of kinetic energy. How else could this thing be moving? What do we think? If I had this same uneven dumbbell, how else could it be moving? Forwards, backwards, up, down, into, out of the page. I'd agree. Imagine, take this thing in your hand and throw it, right? Grab it from one end and just toss it. Imagine like tossing a baseball bat or a tennis racket, right? What happens when you throw those things? It's not that they just kind of float through the air. They spin when you throw them, right? Because I'm grabbing from one end of this thing and I'm throwing it like that. Right? I used to be a little bit more of an edgy teenager and I like to do throwing knives all the time, right? Throwing knives are the exact same thing. You're throwing them, they have a spin to them. Part of the art of that is matching the spin to the distance. But they're traveling both a distance and they're spinning at the same time. That is what we might refer to as a split between rotational kinetic energy, what we have just seen here, and translational kinetic energy. Translational kinetic energy translating, going from one spot to another, as we have known kinetic energy this entire time. Rotational is the new kid on the block. It is an additional place that we could be storing kinetic energy. And I'm going to do a really strange tie-in right here, but any of my chemistry friends, you know, like the 3/2 kb versus the 5/2 kb, for different monatomic versus diatomic gases. And that's the difference between something that's just spinning around or moving around in one place, kind of buzzing around against one spot, or something that's able to start spinning around. There's two directions that a molecule could start to spin around, and so there's an extra 1-2 on top of that fraction. But you'll probably talk about that in a little bit more depth when you get there, including, of course, in 192. We got a lot of cool things to talk about in 192, but we need the basics down first. That's what this class is all about. So, any object can have a rotational motion, have a rotational energy associated with that. It doesn't matter if it's some strange blob spinning around, if it's a group of particles spinning around, if it's a single particle spinning around, whatever it would be. And I'm going to stop using particles necessarily because a lot of the time here we're looking at something that's like a ball, something that has like some real mass and takes up some actual space rather than this nonsense 1D point kind of thing, right? We can start to talk about real objects. 1/2 I omega squared is the rotational kinetic energy of any object. Now, specifically here, when we're talking about this moment of inertia, we're talking about the moment of inertia about the point that it's actually spinning around. In this case, it was spinning around the center of mass, right? Fantastic, wonderful, perfect. But if it is forced to spin around someplace that is not the center of mass, imagine like a pendulum, for example. It doesn't spin around its center of mass, it spins around this point over here, separated from the center of mass. We have to take the moment of inertia relative to that axis of rotation, I of P, rather than the center of mass moment of inertia. But how do we find I of P? What fancy pants equation do we have that can take us directly there if we already know the center of mass moment of inertia? I know we know this one. I believe in us. Parallel axis theorem indeed. That's exactly what I'm thinking of here, right? All of these tools come in and start working together in a very nice way, right? You've got your table of all of these different moments of inertia, and if somebody says, I'm going to poke my stick through this spot rather than through the middle, then you can say, perfect, I don't even care. Right, all I'm going to do is take the parallel axis theorem. It's a really quick calculation. We've got our brand new moment of inertia. We can calculate the kinetic energy. We can calculate torque, angular acceleration, any of these things that we could possibly need. So, let's try this out. We're having some fun with this at this point. Let's imagine we've got a 300-gram ball and a 600-gram ball. They are both connected by a 40-centimeter long massless rigid rod. That is to say, it doesn't contribute any mass, and it's not going to deform. It's going to stay a fixed shape. To make another uneven dumbbell. The dumbbell rotates around its center of mass at 100 RPM. What is the rotational kinetic energy of the dumbbell? And of course, when we're thinking about energy and power and all of the things like that, what are our standard units? They're not rotations, and they're certainly not minutes. So you'll need to do a little bit of a conversion here. But I'm going to say take just the next 3 or 4 minutes, see if we can come up with a number on this one, and then we'll take a look at it together and see what you got. All right, so let's start taking a look here. So of all of the things that we've got, first, of course, we want to start with a fantastic picture. And what does it take to be a fantastic picture? Well, it just needs to be on the paper. Ideally, it's got some details involved as well, but it doesn't really matter too much. Let's imagine 1, let's imagine 2. This is our 300-gram, or better yet, 0.3 kilogram. This is our 0.6 kilogram. Of course, sizes are very accurate. Straight line connecting the two of them. Now, realistically, you're doing this problem yourself. Where's the center of mass? Where do we think? Closer to the 0.6, but I can be even more accurate than that. I know it's going to be closer to the 0.6, but I also know it's 2/3 of the way over. Here's 1/3 of the mass. Here's 2/3 of the mass. So, I'm going to have 1/3 of the length and 2/3 of the length for my center of mass right here. Now, we can prove that, and let's go ahead and do that. We know that the center of mass, let me call this spot right here, x is equal to 0. And then we can call this right over here, x is equal to L for now. We know L's going to be the 40 centimeters, but let's get to that in just a second here. What I'm basically saying here is that I've got, all right, divide by the total mass. I've got 0.3 at 0. I've got 0.6 at, whoops, did that parenthesis the wrong way. I don't know how you do something like that, but that's all right. At L. Total mass is 0.9. That means I've got 0.6 over 0.9 times L. Center mass is 2/3 of the way over. 2/3 of 0.4 should be something just like, what did I have for this thing? If it was 0.4 meters, where is the actual center mass on this one? Oh, I don't actually think I calculated that up. I don't think it's at, it's not 0.24. It's at 0.2, yeah, yikes. So we can use that if we want to. So it's over at 0.2667. We'll call it right there. Meters. That's fine if we want to use that. That's all right. Or I can just leave it as 2/3 and 1/3 L. So, all right. Well, there's where our center of mass is, right? And we can either find that from the picture if we're looking at this thing and we've got a little bit of intuition, or if you're not feeling super confident with the center of mass quite yet, I would recommend trying out this equation. Conceptually, we can see where it's going to need to be, or roughly, right? Just about. If we're not exactly confident on the 1/3 versus 2/3, totally fine with that. We have an equation that will definitely get us there, and I do recommend using that just to make sure that we're all on the same page. We get a little bit of practice with this, because we practice with the easy ones so that when we get to the hard ones, we've already got a little bit of experience. So, I'm looking for the rotational kinetic energy. Here's where it gets a little bit spicy. I am given, let's talk about some of these values. I know mass 1 is 0.3. I know mass 2 is 0.6. I know the length is 0.4 meters. And I know that the angular speed is 100 RPM. And again, I hate that, right? Yikes, 100 RPM, you know, get with the program. That's not the value that we want. We want to convert this into 10.47 radians per second. Radians, seconds, those are standard units. Those are what I'm happy with. So anytime you see RPM, almost immediately, it's a safe bet to just convert it into radians per second. I need to find what this kinetic energy needs to be in the first place, and it just so happens that I have just recently gotten a very nice equation, energy rotational, or we can just do capital K is what we typically use for kinetic energy, isn't it? Kinetic energy rotational. I can say, all right, kinetic energy rotational is equal to 1/2 I omega squared. Fantastic. I've got omega, right? We're almost there. We're most of the way there. But we need to first find the moment of inertia. And we know that it's spinning about the center of mass because, well, that's what it says, right? It's spinning around the center of mass. That's how things that are not pinned in any sort of way would like to spin. So, with all of that in mind, we can say, all right, well, then we need to find the moment of inertia about the center of mass. It is not one of our fancy special cases, right? So what we're going to have to do here is we actually have to solve this out for ourselves. But that's all right. It's not going to be too bad. Let's go ahead and highlight this orange. Say we need to find this first. I'm going to take these quantities right here. Remember that the full equation, I should be equal to the sum of every single mass times every single radius squared that it is away from where we are spinning around. Long and short of this is that this should be essentially mass 1, R1 squared, plus mass 2, R2 squared. Right here, I've got my R2, I've got my R1, I've got my two masses. Plug these things in. I'm going to leave it as mass 1 for now. Just symbolically, it's a little bit cleaner, but this is going to be mass 1, 2/3 L squared, plus mass 2, 1/3 L squared. At the end of the day, we plug all of these things in, and what we should find is a number something like 0.032 kilogram meter squared. We have our quantity for I, we have our quantity for omega. All we need to do now is plug those two in, and we should get that our rotational kinetic energy is something like, where did I draw this number? 1.754 joules. And how are we feeling about all of that? We found the center of mass to prove where it is, right? More than anything else, we wanted to show that it's right here, 2/3 L. That was our big play. We wanted to make sure we could conceptually kind of see where this thing should be, but it was very important to us that we actually made sure to confirm that, right? That the equation actually backs up our intuition here. Now, as we're finding this thing, sorry, I've been trying to fight with the, you'll see these extra little marks, like the extra little tiny dots and everything else. Sometimes my pen gets out of line on this one. And I have to, like, reset the tip to make sure that it actually doesn't keep doing that the entire time. But, yeah, so for any of that stuff, I know you've said that you've got it, but at this point, what we would be doing is we're essentially just taking the coordinates of these things. I want to figure out what is the distance between this and this. So I could have taken it's 0.4 away, or it's, at x is equal to 0.4. I need to find how far it is from the center of mass. So that's where that would have come from. So let's keep moving for now. Our definition of static equilibrium has to expand a little bit. Right, so far we know static equilibrium is when all of the forces are zero, or all of the forces rather cancel out, the net force is zero, and we have no motion. Rotation, I'm not moving anywhere in that same sense. There's no translational motion. It's not going from A to B, but I'm still going to argue that it's still moving. Right? You might argue that a rotation is a dynamic equilibrium, and I could agree with that. But for our true static equilibrium now, what we have is zero net force, zero net torque, zero velocity, zero angular velocity. All of those things must be true for us to be in what we call static equilibrium, right? We look at that thing and we should agree that it's completely still. It's not doing anything, and it's not about to start doing anything. So, some notes on gravity. This is going to be a little bit of an interesting one, but as we have been looking at these things the entire time, what have we always done with gravity? How have we treated gravity? A particle or a box has gravity acting on it. How have I treated gravity this entire time? Does anybody remember? I made some point about this a while ago, but we've kind of ignored it ever since. What is gravity doing? I don't consider the fact that the box has a real mass and is actually, right, if I were to draw out a real physical box, or I can even take a shape. I was looking for my pen holder and I had it in my hand. Let me take my mug, right? I love this mug. Fantastic, wonderful. It's got mass distributed throughout it, right? It is not just one single point full of mass. I could argue that there is some gravity pulling at this handle, just as there's gravity pulling on the rest of it. I'm not breaking my mug. I love this mug. But I don't treat it like that. Most of the time, when I'm thinking about, okay, well, I want to have the mug going, if it falls, if it slides, anything else like that, I don't think about the individual pieces of my objects. When we're talking about a crate sliding along the floor, I'm not looking at every single board that makes up the crate in the first place. What I'm doing is I'm saying this entire thing is acting like it's at one point where all of the mass is at that one point. And I'm not breaking anything here. I don't have anything to break. Take that pent-up rage somewhere else for now. So, technically speaking, gravity acts on the entire object. However, effectively, it's only pulling at the center of mass where we're going to assume all of the mass is located. And I can prove that one with a quick example right here. I'm not going to break my book, but I can take this book and I can start sliding it off my desk. There's about an inch off the edge. I can slide it a little bit more, right? And we can get pretty far the way over there. Right there, it's tipping point. When does it start to tip? If you've got a ruler in hand, if you've got a ruler nearby, try this yourself. See, where's the last point right about where that ruler stays on the desk? We're right that it's when the center of mass goes over the edge. But this is a really cool thing with a ruler because you can really calculate this thing out, right? If right at 6 inches it starts to tip, or right before it starts to tip, that's my whole point right there, right? 6 inches is right around the middle of the ruler. It's as if gravity is acting only on the very center of that object. And once it goes over the edge, right, now our pivot point, the edge of the desk, is here, and gravity is over on some edge. Now we have a torque, now we start to spin, now we start to fall off. So, this is a little bit strange, right? But this is how objects work. It's not that there is necessarily some big sweeping generalization that we're making. Not quite yet. We'll get into that sweeping generalization later. But for the most part, this works out very well for almost every single object. Gravity pulls as if it's all localized at the center of mass. And we can use that, and that's a very important deal here, because this entire time so far we have been looking at things that the forces acting on them are whatever the forces acting are. But gravity is an important one because, of course, we have dealt with gravity plenty, and we're going to continue dealing with gravity. Gravity is here to stay. For all of the objects that we're looking at right here, you'll notice that I have been saying center of mass the entire time and not the center of gravity. Why is that? I'm saying here that they're mostly the same, but why might an object not have the same center of gravity as it does the center of mass? This is foreshadowing more than anything else right now. We haven't talked about this in depth. But I have brought it up once or twice that 9.8 meters per second squared downwards is not actually like a universal constant. Even if it has a non-uniform density, all of these things still apply, right? It doesn't matter because this mug does not have a non-uniform density, or it doesn't have a uniform density. It's, you know, the handle over here is, you know, arguably much smaller mass than the rest of this thing. The center of mass, even if this thing were to be made of different materials, I would still argue that the center of mass, wherever it is, somewhere like right here in the middle of the mug, gravity still pulls as if it's pulling right at that one single point. So that's not the deal here, but it's the fact that gravity doesn't actually, it's not actually a uniform force. That's a big deal. When we're talking about that 9.8 meters per second squared, we're talking specifically on the surface of Earth, right around the elevation that we're at. If you go up to where the International Space Station is, G is a little bit less. It's somewhere, I think, around 7 or 6. Maybe it's 8, but it's a little bit less. It's not the same quantity that we feel right here on the surface. So, most of the time, because essentially anywhere where we're using 9.8, the center of mass, center of gravity, exact same concept. The only situation that we would have to get into where that might be a little bit different, imagine like, has everybody read enough sci-fi or seen enough sci-fi things to know what a space elevator is? The idea behind a space elevator is that a sufficiently advanced civilization that can get their shit together can build a very, very, very tall elevator. It's a very long-standing vertical structure that essentially just takes us up into the upper atmosphere. Very useful for, you know, now you don't have to send rockets all the way from ground level. You can start them from some platform that's way up. That is the type of object that I would consider to have a slightly different center of gravity than it does a different center of mass. Because the center of mass, of course, if it's a big tube, it's going to be right in the middle. But because gravity is just a little bit stronger at the bottom than it is at the top, the center of gravity is going to be just a little bit closer to the Earth than the center of mass is. Does that all kind of make sense? It's also why, for the most part, we're not going to worry about that difference. You've got to be like large structures. Maybe skyscrapers are starting to get there, but not a house. Right? Not even like a 3-story house or anything else like that. I would argue no building in Oxford would ever have to worry about that difference. It would be so incredibly minute that it's not anything for us to worry about. So, with all of this in mind, our to-do list for brand new problems is getting a little bit larger here. A lot of these things, what you're going to have to do, of course, we always draw a good picture and a good description to go along with it. We want to draw out our axes, and now we might also want to get in the habit of starting to show clockwise versus counterclockwise. Which direction do we call positive rotation? Draw a free body diagram if you need it. If you're doing this with static equilibrium, you'll know that the F net and the torque net should be 0. Right? From all of that information, you can start to solve some of these things. And then, of course, we have our squad high five at the very end, which I will not perform right now. But we'll get to once we solve the next problem, right? That's our last step here. So let's go ahead and try this thing. Let's imagine I have 2 blocks of citrine, which is a very beautiful, precious gem. Or I think it's a semi-precious, technically. But that's pedantics more than anything. They have a uniform density and are balanced on the pivot. Where do I have to put that pivot? Where along the x-axis do I have to put that pivot so that they are balanced? Use our knowledge here of torque, of net forces, to figure out where do I have to put this thing so that the torque and the gravitational forces everything sums up to be 0. And I'll give you a hint on this one. The forces really don't matter nearly as much as the torques do, because that pivot's going to provide all the normal force that we need regardless. So focus in on the torques, but I want you to take the next, say, 4 or 5 minutes to work on this one, and then we will take a look all together. All right, team. So let's go ahead and start taking a look at this. Here's what we've got. Right. There's a couple different ways that we can actually imagine looking at this one, but I'm going to focus on the torque method because realistically, most of your problems are going to depend on torque. What's another way that I can imagine doing this, though? Does anybody have so I'm saying the balance the torques, that's one way to do this. What's another way that we could feasibly try to do this problem? Does anybody know? Find the center of mass. That's a good way to do this as well. However, it doesn't always work quite in the same way, right? Because as I'm about to show in the next example, center of mass does not always get you all the way there. In this problem in particular, though, that is one way to do this. I would say if I know where the center of mass is and I treat it as one solid block rather than 2 individual blocks, then my pivot directly underneath the center of mass, I should find a balance. So that is one way to do that, but I do want to walk through the torque method because we're going to be using the torque method more often. Let's start by, of course, stealing this picture so we can draw all over it and figure out some things that we can do with this. And I think I'm actually going to blow this up just a little bit so that we can actually draw on this with plenty of space. Here's what I'm thinking, though, right? This is fine on its own, I guess, but what I really want to do, I have already told you where should we put this pivot point. We say that the pivot point should go right around here. And the symbol that we'll typically use for that, it's like a combination of the in arrow and the out arrow, dot, X, circle around it. That says right there, we're pivoting about that point. So, draw a free body diagram. That's a good thing to do here. What I'm going to do is I'm going to say, all right, the bottom block has a little bit of a lower mass. I'm going to call that lowercase m. What force is acting because of lowercase m? Well, it's going to be acting right on the middle, center of mass. This thing is 2 meters long, so right here at 1 meter over This is where I'm expecting to see little mg. My bigger block, 1 meter across, right here in the middle again. These are not particularly straight arrows, but that's all right. Capital MG. Now, thinking about torque, I need the distance, the force, and then the angle between them. Luckily, the angle between them for both of these is just 90, so I don't need to worry about that. And technically speaking, I am neglecting the normal force. The normal force is here as well. How do I even begin to talk about where each of these forces are acting, though? It's not D. It's not 1 meter. It's not 2 meters. It's... Yikes. This is kind of rough. Here's what I'm going to do. I'm going to say, you know it would be so much easier if I had these quantities instead. Let's go ahead and call this, I'm going to call this distance right here R1 between the pivot and the force, and I'm going to call this distance right here R2. Does that seem a little bit easier to deal with in torque? I would think so. That seems easier to me. So let's go ahead and solve out with this, and then let's come back to this later and try and figure out, okay, how do these things actually relate to the variables that we care about, right? Let's go ahead and focus on that, though. So we are given lowercase m, that's my 1 kilogram. Uppercase m, that is my 4 kilogram. I know that the entire thing is 2 meters long. I'm not going to try and write all these details out because I think it's better written on the picture here. But I do know one important detail is that the net torque is equal to 0. So let me start there. I said this is probably the spot that we want to focus in on. Torque net. What contributes to that? Well, first, let me go ahead and look at this force right here, mg. I would say, okay, with all of that there, it is the force, mg, acting at a distance r1, and then it's perpendicular. So there's no, it's sine of 90, essentially, right? It's just 1. Okay, great. And it's going counterclockwise, so I'm going to call that one a positive. What about the clockwise force? Well, this one is just going to be mgr2. All of that should equal 0 altogether. Cool. All right. Well, let's simplify this a little bit at least. I can get rid of all those g's, and I can simplify this to say mr1 is equal to mr2, capital M, of course. I've run out of things that I could use this for. This worked really well for setting this problem up, and this conceptually made a lot more sense to me, right? Lowercase mg was r1 away from the pivot. Uppercase mg was r2 away from the pivot. Perfect. Fantastic. Now, I need to look at some of these distances. Let me talk about r1 first. Where's r1? How do we relate it to some of these other things? So let me start. This is going to be my start point right here. Label this start. I am going to go this distance. And what is that distance right there? How long is that line that I've just drawn? One meter. Yeah, so let me redefine this and say, all right, well then 1 meter plus r1, that gets me to a distance d. Now I'm going to do the exact same thing with r2, but this is going to be a little bit strange at first. Okay, so I'm going to start with d. I need to figure out, okay, I need to find some way that I can relate to what r2 is going on here. One of the values that I see kind of coming out across to me right now is this distance right here, which that should be half a meter because it's splitting the upper block halfway through, right? So the upper block is 1 meter across. I split halfway across. That's 0.5 meters. So that's basically saying that 0.5 meters plus R2 plus D, go ahead and write these out. 0.5 plus R2 plus D, this should equal the full span, the full 2 meters. So I'm going to use these two expressions. I'm going to say R1 then should be equal to D minus 1. R2 then, I'm just solving these things out. R2 then should be 2, or rather 2 minus 0.5, 1.5 minus D. Now, this is a strategy that I have not talked about too much because it hasn't quite been applicable to us yet. But if you have ever been in my office hours or seen me working on problems, a lot of what you'll see me do is essentially I just draw out a picture, I start throwing variables onto it. Whether or not I have the variables, I just go crazy and start drawing variables on this thing anyways, because every single time I'm drawing a variable, I'm saying essentially, I think this might be useful. I have not bothered to check whether I have that value or not. If I have the values, I will make sure they show up on the picture somewhere. But even if I don't have the values, I might just give it a name on the picture anyways, because I might say, I might use this later. It might be useful for me, and I'm just kind of like grabbing things, solving problems as I go along this thing. It might be useful for me to grab that, use it conceptually, understand where the equation is going to go, and then come back later and come up with some sort of expression of how does my variable fit in the big picture. R1, R2, this is how they fit into the big picture. So now I'm going to take these two equations, and I'm going to plug them in. That could have looked a little bit cleaner. Right here. What this is going to become is m times d minus 1 is equal to capital M times 1.5 minus d. Point. Might as well throw in these numbers at this point. Little m is 1, big M is 4. So this is going to become d minus 1 is equal to 6 minus 4d. Then I can rearrange this just a little bit more. I would say 5d is equal to 7. Final result, d is 1.4 meters. And there we have it. So I think this was a more complicated method than simply finding the center of mass. However, finding the center of mass is not always a viable strategy for problems like this. So I did want to go through the torque method anyways. Sure. R1 and R2, I have said that I am probably going to be pivoting around my pivot point. If this thing is going to rotate one way or the other, it's probably going to do so around that point. So then I look at all of the forces and where they are relative to my pivot point. This is my R cross F, or RF sine of theta, coming in here. Except I didn't know these R's, they're not written anywhere in the picture, so I've decided to add them myself. The 0.5 down here. 0.5 comes from the fact that the top block is 1 meter over. Force capital mg is right at 0.5 meters over. That's 0.5 right there. To get the rest of the way to the pivot is R2, and then I take d the rest of the way to make it the full 2 meters. It should be in the center of mass, right in the middle. All of these things are a uniform density, so if it's 1 meter long, I know the center mass is right smack dab in the middle. So, there are some easier ways to solve this problem, and there's going beyond just what goes into dealing with, where we put the pivot point is another place. We can also look at the center mass. That is an easier way to solve this one, but where we put the pivot point can make this problem, I think, a little bit easier depending on how you're looking at it. I think, though, that this is probably the intuition most of us had. We would say, okay, well, if this thing, we have all tried to balance things. We try to balance a water bottle or a pencil or anything else like that, right? That's like the name of the game, is you're trying to balance things, because what else are you going to do in school? So that's the intuition that I went with in this problem. However, let me bring up one of those earlier points that I said I was going to get back to, right? A little bit of backtracking here, if you will. If this thing is supposed to be not rotating, if we have specifically said no rotation, then I would argue that whether we had picked this point right here in the middle, okay, well, it's not supposed to rotate around that point, fine, whatever. Well, then similarly, it shouldn't rotate around this point either, right? It shouldn't rotate around this point either. It shouldn't rotate around this point either. It doesn't matter which point I take. It shouldn't be rotating. the net torque around any of these points should sum up to be 0. And oftentimes, we have this choice. In problems with static equilibrium, we can choose what we call our pivot. And I think, honestly, one of the easier ways to solve this, if you're still using torque, is to not take this middle pivot point, but it's actually to take this point right here. Because if you take this point right here, suddenly we don't need R1 and R2. We see lowercase mg is acting 1 meter away. The pivot is acting d away. Capital Mg is acting 1.5 meters away. How much is the normal force in this problem? What does the normal force need to be doing? What's its job here? Any guesses? Mg plus Mg. Yeah. It better be holding up those two forces, right? Because things better not be moving. So normal force is, I don't want to say trivial to find, but it's pretty close. That's not a hard thing to calculate out. And then we have all of the things we need. Now our torque equation has 3 terms. We have added an additional term by doing this, but the way that we talk about each of those terms was simpler. So I bring this up because now when I keep talking about how there are multiple ways to approach a problem, we have expanded the number of ways that you could approach a problem. We now have even more ways that we could approach a problem. And that kind of openness, how we can calculate some of these values, can be paralyzing, right? What do you paint on a giant canvas? It's really hard to decide. So I have a little bit of respect for that one, but I want to try and show you some of the different ways that we can choose some of these points to make these problems a little bit easier on ourselves. Now, I do see one comment of why couldn't we have done something like R1 plus R2 is equal to 0.5? My problem with that is that we could have done that, but then we would have just been subbing in and solving for either R1 or R2. I was interested in D, so I wrote out these equations to solve for D. That's specifically why I did these two. R1 plus R2 being equal to 0.5 is not incorrect, but I think it's more steps than it's worth. So, what was our final step of the problem-solving process? What did we actually have on that one? We have drawn the picture, all of the other things, squad high five. Slap it right there. All right. Excellent work. Your first torque problem. So, let's go ahead and keep working on this stuff. Let me show you an example of one of these common things. And if you are ever on Twitch, you will notice this picture is floating around there in my big page up top. Ye Old Physics Shop, somehow still in business, is looking to get a bigger sign, right? They have decided that maybe business is not quite as good as they would like it to be. Let's get the advertising out. Because surely if people saw Physics Shop, they want to come, right? So maybe they just can't see the sign. But here's what we've got. We're trying to design some sort of sign that is 120 centimeters wide, hangs from a 5 kilogram, 200 centimeter long pole, right? So we've already got essentially this support structure set up, and we have an idea of how big we want the sign to be. But we're trying to figure out what material can we make this thing out of. What is the maximum mass of the sign if the maximum tension of the cable is 300 newtons? So here's what I'm going to try and do. Of course, I'm starting with a picture. Now, for something like this, there's a few different ways that you can approach these things. And this is a little bit of a strange kind of situation. One of the ways that we can consider this, and how we could have considered this problem as well. Oh, I forgot to point out something on this one. Let me come back to this problem just a little bit, though. Let me finish my description, then we'll come back to that problem and talk about one last method here. Oh, my picture went to the middle instead. Here's what we've got. That's my picture as I would see this thing, and I'm even going to blow this thing up just a little bit more. I want plenty of space to actually draw on this thing. Pixels be damned. So, where is this thing spinning around? Is it spinning around anywhere? What do we think? We could argue that it attaches to the wall and it would spin there, right? If the cable snapped, I think I would agree with that. It would probably spin around right there. But realistically, if it's not spinning, does it matter where I call my pivot point? I don't think so. I don't think it matters at all. Because my net torque around this spot should be the same as my net torque around this spot, should be the same as my net torque around this spot. It doesn't matter where I look. If the object is not spinning, the net torque, regardless of where I look, should be 0. And that's a really important point, right? And that's why we're focusing here on static equilibrium problems, because this offers up some more options for when we're actually going about solving the problem. So here's the kind of situation, right? Let me draw some of the forces that I know on this thing so far. Let's do that. I would say, okay, well, this, like the 200 centimeter long pole actually has some mass, right? As annoying as that might be. So I'm going to say, all right, well, there's a mass of the pole, mp times g. Gravity pulls on that. There is the mass of the sign pulling over here like this. Call it ms times g. And then there's this cable attaching these things, so I'm going to expect to see a force right here as well. Call it t. So my connection with the wall, what direction does my force need to point? What do we think? I know that if I'm in a static equilibrium, net torque is 0, and that's usually one of the big spots that we're looking at right now, but so is the net force. So where do the forces coming from the wall need to be actually pointing to make this happen? Any guesses? So as I'm looking at this thing, I see 2 down forces, and I see a force pointing up and to the left. Now, I don't know this for certain. I'm going to take a wild guess that it's probably also pointing up, because that seems to make sense to me, right? It's got suspension on both ends. But then also, because the tension's pulling to the left, it has to point to the right like this. So there's this weird, like, attachment force from the wall pointing up like that. And what forces do we know things about, right? Which of these 4 forces do we actually know some details on? What are our given variables here? Do we know any of these things? We have essentially our maximum tension. We are looking for the mass of the sign, so that's kind of in a given thing, right? We're definitely working with that variable, and we also know the mass of the pole. I don't know anything about this right here. All I know is it's there. It's some sort of normal force or a hinge, or I have no idea what it is. It's attached to the wall. That's all I know. And I don't know what direction it points. I don't know what its magnitude is. I don't know anything about that force. So if we had to pick a pivot point, if we were forced to, if we said, all right, we need to pick some pivot point, we need to say, we know this thing isn't rotating, but we need to look at one place where it feasibly could be rotating around. The spot that I'm going to pick is the one that makes the problem as easy to solve as possible. And in this problem right here, that's right at this spot. My pivot point is there. Now, the torque from my mystery force, 0. It doesn't matter. It doesn't show up in the problem anymore. I'm done with it. We don't need to worry about that force anymore. Now we can focus on the other 3 forces that we either already know some details about, or we're looking for that information in the first place. So, let's go from here. I'm not going to focus on net force very much, because net force would require me to figure out what my mystery force is. And I can already tell you, if I have one mystery force and I have another mass that's also a mystery, I'm not going to find my mystery force. That's 2 unknowns for one equation. It's just not going to work out super well for me. So instead, let's go ahead and start to take a look at this from a torque perspective. So I need to figure out some values here, and let's go ahead and do this. I'm going to call my 3 separate values. So I'm measuring all of these radii from my pivot point right here. I can say that my net torque should be, let me start from the pole, the mass of the pole, the gravitational force from the pole, the radius of the pole. And that should have a minus sign up front because it is trying to send us clockwise. Same deal for the sign. Wherever the sign is at, the mass of the sign, the gravity force of the sign, the radius of the sign from my pivot point. And finally, of course, I have my cable. My cable is just going to be some sort of tension, the radius of the cable, and what else? What's the last thing that I actually need here? What am I missing? Sine of theta. I am taking the approach on this thing. I'm not dealing with the big, the XYZ full determinant matricy, that kind of nonsense. I'm taking the easier way, assuming that I know the magnitude, the radius, and the angle between the two. And then I look at this and I say, hey, this wants to spin me counterclockwise, right? I don't even need right-hand rule for this one. I could say, I can see from the picture, it wants to go counterclockwise. So I know it's going to be a positive. All of this equal to 0. Now I look at all of these things. I say, all right, I just need to find what these quantities are. I would argue that the pole, that radius right there, center of mass, right? So radius P should be equal to, 1 full meter. Where is the center of mass of the sign? Well, the whole sign is 120 centimeters across. So I go my first 80 and then I go halfway across, right smack dab in the middle right here. This is 140 centimeters, or 1.4 meters away from the wall. Finally, my cable is the full 200 centimeters, or 2 meters. Then the only other thing I need for this whole big equation right here is theta. And of course, that one's an easy one to find here. We're just going to use a little bit of trig. I'm going to say theta is going to be the inverse tangent of opposite over adjacent, 250 over 200. I'm running out of space here. Theta should be equal to some quantity like 51.34. Not a given variable, right? I want to point that out. Theta was not a variable that we were given on this problem. But I look at this thing and I would say, hey, theta would be a really useful variable if we did have it, so I'm going to use it. How did I find R of P is equal to 1 meter? Because I know that the full pole is 2 meters long. The center mass of that thing should be right smack dab in the middle. R of C, the rope pulling full 2 meters away from my pivot point. So with all of this stuff in mind, we have every single quantity we could need except for the one that we're looking for. We're ready to solve. M of S will be equal to, this is going to get a little bit nasty here. If I actually write this thing out full, I could argue that this is probably a little bit overkill. But that's all right. This could be worse. Whoops, not R of P, R of S. But I have every single quantity in this equation at this point, right? All of these things are given to us. So when we solve all of them out, we should find that the maximum mass of the sign that we could have is 30.577 kilograms. If we go any over that, the cable will snap. How did I find R of S? Same deal. I know that the center of mass of the sign is where gravity is going to be pulling on it. I know that from the wall to the edge of the sign is 80 centimeters. I know the sign is 120 centimeters all across, so I've got my 80 plus the 60 to get right to the middle. But all of these things, I need to essentially just look at the picture. I need to figure out, okay, where's the center of that object? That's where gravity is acting. So, something like this is a wonderful thing. They don't tell us anything about where the pivot is, right? That is for us to decide. And what I want you to do is try to look at some of these problems and figure out, where's the best place to actually put that? Where can I put this and have it be as useful as possible, right? Either to eliminate as many things as I could possibly have, or to eliminate those things that I don't know, that I don't have any good way of knowing. So, of course, as we're going through all of this stuff, now it's up to you to try the same. This is going to be a little bit different. But let's imagine here a circumstance using conservation of energy. Find an expression for the time it takes for a solid sphere to roll down an incline of length L. No rolling friction, but it's not slipping. Right? So there is technically friction on the slope. I want you to understand that. There is friction on the slope. There is no rolling friction. Because if there was no friction at all on the slope, then the sphere would not turn. It would just slide down. So this is a real object. This is something you can experimentally demonstrate yourself. This is taking any sort of tennis ball down a plank of wood or any incline like that. And what you're seeing is that this thing kind of catches and rolls just like a tire would. I want you to think about what would conservation of energy look like in a problem like this. Where does all of the energy go? If we were to solve this thing out as a block, how would that look? How does the sphere compare, knowing that the sphere will start spinning? So, I want you to go ahead and spend the next, say, 5 or so minutes on this one, 4 or 5 minutes, and then we're going to take a look at this together. All right, so let's start to take a look at this one. And also, if you have realized, this is essentially a proof, an answer into looking at why was it that the sphere wins the race against the cylinder. In short, it's because the sphere has a smaller moment of inertia. It's easier to get the sphere to spin. Because as any of these objects rolls down, and again, I do encourage you, go ahead and try this. Any of your things at home or anything else, try to see different things rolling down inclines, see what the differences are like. For all of these things, what we're seeing here is that for it to be moving down the slope, it not only has to have a translational velocity, a linear velocity, it also has to have a rotational velocity because the way that it actually propagates forward is through rolling. So, when we're looking at it like that, let's think about how this is going to go. I'm going to say, okay, so we have some sort of slope. We have some sort of sphere. Let's try and make that look like an actual sphere. To be going down the slope, and this is a length L, as we would need it, to be going down the slope. Do I have any information about the incline here? No, rolling friction. We're missing a variable, aren't we? We certainly are missing a variable here. We need to have theta. Somehow I forgot to write that in there. That's all right. We need that angle theta, right? Because we have the length of the slope. We don't have the height of the slope. So what I know is that as the sphere starts to go down, it is going to start rolling like this. Some omega. That's where it's going to be propagating down the hill. So in terms of that, let me just think about it like this. Let me go ahead and say that this is some sort of height h. I'm going essentially from where it starts down to where it is right here. All of the energy that it starts with, it started at rest. So all of my initial energy, let's go ahead and label these two columns, initial versus final, what we're seeing here is all of my energy started as an mgh. All of my energy ended up in either rotational kinetic energy, 1/2 I omega squared plus 1/2 mv squared. Translational energy. And this is exactly what I'm talking about again. Imagine throwing a tennis racket, right? The tennis racket is not only translating forward, but it's also spinning while it does so. In this case, though, right, assuming that this isn't slipping, it's not just sliding around or anything else like that, assuming that it's not just slipping in place, it's actually continuously rolling down the hill, then what we should be seeing is what? What's the relating factor between my rotational and my translational kinetic energy? What do we think? What is there connecting the two of them? How fast can I actually go down the hill? Any guesses on this? I can only go down the hill as fast as I roll. Because if this thing is not just sliding down, if it's actually sticking to the surface as it rolls down, then my omega is directly proportional to my velocity. By that equation, v is equal to r times omega. Think about what goes on with the surface. Let's do like a real deep dive zoom in of this thing, right? If we were to see this surface, and I'll draw this thing really big so that we can actually see it, and then I'm going to erase half of that because we don't need to see the whole thing. Only looking at the actual spot that is in contact here. If I know that the full thing is attached, my rotation goes like this, omega. My velocity going forward is based on this omega. Looking to the top of the block is a little bit easier here, but I'm essentially looking at how this surface of the block moves relative to the ground, right? Because remember, rolling motion is a little bit strange. The friction goes one way and the velocity technically goes the other, but the whole shape goes forward, right? Think about the way that tires spin. Technically, the part that's in contact with the road goes backwards, but that's because it's propelling the rest of the shape forwards. So right here, that's exactly what we're seeing. This outside edge, being, of course, v is equal to r times omega, is what's actually in contact with the slope, is what's actually rolling us along the slope, along the surface. That means that I can go up to this equation right here, and I can say, all right, well, let me go ahead and plug in. This side is going to become first. Let me plug in for my I. This is going to be 2/5 m r squared times omega squared. And what are we looking for here? Find an expression for the time it takes for a solid sphere. Okay, so I think I would probably like to deal with velocity, right? I would say length divided by... Did I do this right in the first place? Did I do some weird things here? Let me see if we actually even need theta. Let's take a look for a second here. Plus 1/2 mv squared. R squared times omega squared is v squared, as we would see it coming from right here. So this is going to become the 1/2 cancel out. I've got 1/5 mv squared plus 1/2 mv squared. Now, if we had been doing this with a cylinder, this quantity right here would have instead come out to be 1/4 mv squared. It would have taken a greater portion of the energy, and that means that it would have less energy left over for the translational velocity. Right? And I know this goes a little bit backwards. One of the concept checks that you guys had was essentially which one has more kinetic energy as it's rotating around. And that's not saying something that's contradicting this. What this is basically saying is we only have so much energy that we can actually pull from. It needs to be distributed both into the rotation and into the translation. So if the rotation is going to take up more, that is, if there is a larger moment of inertia, then I'm not going to have as much left over for translation. So all of this stuff together, this is going to turn into a slightly nasty thing here. What is this? 2/10 plus 5/10. So this is going to become a 7/10 mv squared. 7/10 mv squared. The m's cancel out. I'm solving out for the velocity because I'm looking for the length, the time it takes to get down to the end of the slope. Energy conservation is the best way to do this as well because the acceleration description is wonky. I've got a warning for you on that one. So I would say, all right, well, this is going to become GL sine of theta is equal to 7/10 v squared. This is, of course, my final velocity down at the very, very bottom of this thing. So I could say that my velocity as we get down to the bottom, Vf, let's just call it like that for now, is going to be 10 GL sine of theta divided by 7, square root of that for a competition here, an entry into the competition of most disgusting numbers of all time. Find a quantity for that, and if we actually do that, we don't have a number for that one, right? Yikes. Did I do something a little bit strange here? 10/7. And, oh, whoops. There should be a 2 right here, shouldn't there? Catch me on those if you ever see them. Remember, because I took no, I did that right. That was all correct. There shouldn't be a 2 there. Wonder what I did in that. I think I did something a little bit strange in one of my solutions here. GL sine of theta, that is just my replacement for H. L sine of theta is my replacement for H. Yeah, this is a little bit wonky. I should have had some sort of quantity theta in here. So with that quantity now, what we could say is that my average speed, if we wanted to do it like this is an average speed as we go through this entire thing. That is one way to consider this. The other way to consider this is, that's probably the best way to consider this, realistically. Average velocity is equal to V final divided by 2. Total length L divided by average velocity should be my time. Those symbols can plug in there, but that's going to look kind of nasty. This is beyond the point where I would have plugged in numbers if we had them. The main part that I really want to focus on more than anything else, though, is that what happens to our energy conservation when rotation gets involved. So think about some of our other problems. Like if you were here right at the beginning, we talked about a collision problem where I had a ball hanging from a string and another ball came in and collided with it, and then that thing was in rotational motion. Why didn't we talk about rotational motion there? Why were we fine to use essentially a transfer? That ball had a kinetic energy, a translational kinetic energy, going up to a potential energy. Why does that work? Why didn't we need rotation for some of those other things? Or any of our, some of the problems when we're thinking about like the pendulum or anything else like that, the thing that swings around and gets caught on a little hook on the bottom? What about those? Weren't those rotational? Why didn't they count? Why didn't we need all of this information for those? Do we have any ideas? I would argue that the object is spinning, though. It's not like, so the ball on the end of the rope isn't necessarily spinning, but it's still a circular motion, and if we look at some of our other problems here, it should still apply. The difference is, how did we actually get to defining rotational kinetic energy in the first place? At the very beginning of this lecture, we talked about rotational kinetic energy is essentially just what happens when I take my regular translational kinetic energy and I convert it. Now, the reason that we like to separate out rotational versus translational, because if the velocity of each object was like this and like this, if it was moving to the right or something else, that's disgusting. That's really rough, right? That's actually really, really terrible, really, really fast. So it's much easier for us to consider rotation separate from translational, right? I've got translational of the whole thing, and then I've got rotation of the individual pieces around the center. But realistically, they were included there. We could have just as well used rotational kinetic energy. It's just that wasn't a tool we had in our belt at the time. But rotational kinetic energy is derived from kinetic energy, translational kinetic energy as we already know it. So we were considering it. We just were considering it in a slightly different way. So, with all of the madness from this stuff here today, how are we feeling? Are there any questions? Is everything kind of starting to connect here? If it's a little bit wonky, that's all right. It is a little bit wonky. But how are we feeling about going and tackling some of these things on our own? All right. Again, a non-Newtonian feeling I will absolutely take. If we are semi-goo, head is not empty. Head is full of physics. We're ready for this stuff, I promise. So, in need of more sleep, I can certainly appreciate that one, though. So rest a little bit easy. There's no homework due tonight or anything else like that. Again, trying to give a little bit of a break here for everything that we've got. That does mean the next one's a little bit longer, but hopefully that's not anything too crazy or anything else. But these new problem-solving methods, I know we haven't explored them quite a ton yet, but in particular, this one is a fantastic for that. Ye Old Physics Shop is another good example of where we're essentially, we've got more freedom now. Right? You're kind of like off the reins at this point. You can solve these problems how you want to choose to solve these problems. You can do that in any way. One of the alternative ways that we could have solved out this problem is we could have said the pivot point is right here and then solved out with 3 forces, and that would have been totally fine. We could do that, but it would have been more work. What do they sell in Ye Old Physics Shop? Classical physics stuff. That's why it's old. Nothing from the 20th century. They sell Bunsen burners, not perpetual motion machines. We had figured that one out already. Old heat engines. I don't know. Other things like that. I'm drawing a blank on this one right now. Do they have massless pulleys? Of course they do. What physics shop would be complete without massless pulleys? But I am confident in you all now to go forth to try out some of these problems. But I realize that we are getting into a little bit more, being in a little bit more free form. It's kind of like painting on a giant canvas, right? It's a little bit more paralyzing when you've got more options like that. So don't be afraid to reach out to me. If you're not entirely sure about your solving method or how to approach a problem, you're, of course, always welcome to send me an email, get in touch, all of that good stuff. Don't be afraid to chat with us, and we can figure out what to do to make your solving a little bit better, make it a little bit more efficient, get you all the way through these problems. But that's all I've got for the end of the day. Have a fantastic weekend, and we will come back next time and dig through some stuff.